So now we have a set of variables that we can use to describe linear or translational motion. And we have a set of variables that we can use to describe rotational motion. But if we have a system like this, right, so we're thinking about some object, some extended object as it spins, and we want to think about, say, some point P on this wheel as it rotates around. There's a way to relate the translational motion of point P to the rotational motion of the wheel. And so that's what we want to talk about in this video. The first thing we're going to do is we're going to relate the arc length S and the angular displacement delta theta. The arc length is just what distance along the circle does point P move as the wheel rotates through some angle. And so you can see that if r here, little r, is our distance from the axis of rotation. Again, that's not the radius of the wheel. It's just the distance from the center of the wheel to where point P is. The arc length relates to the angle that the wheel is rotated through by basically taking S equals r, that distance from the axis of rotation, times the angular displacement. Interestingly enough, S is a length. It has units of meters. R has units of meters. Delta theta has units of radians. And again, this is one of those places where, as an SI unit, radians can sort of disappear when we don't need it there anymore. And so this is one of those spaces where we don't say that S has units of medians times radians. S just has units of meters because effectively radians disappears as an SI unit. So I can also relate the linear speed v and the angular speed omega. Point P, again, is moving at some speed. It's moving with a velocity that's tangent to the circle that it's moving around. The equation that relates the linear speed v with the angular speed omega is very similar to the one relating the arc length and the angular displacement. It's basically the linear speed is just the distance from the axis of rotation times the angular speed. And again, this is meters per second over here is meters times radians per second, where the radians disappears and you're left with meters per second. So again, units wise, this works out because of that unique property of radians as a unit. I can relate the linear acceleration a and the angular acceleration alpha. And so let's say that again we have some linear acceleration that points off in this direction. Well, part of what this tells me is point P, as it rotates around, has to be speeding up because there's both a component of that acceleration that points towards the center of the circle that's keeping it moving along the circle, and then there's a component of the acceleration, the linear acceleration, that points in the direction of the velocity, which tells me that point P is speeding up as it spins around. That means that there are two components that I want to think about. And of course, I don't want to think about those components in terms of the way that we typically think about positive x and positive y. What I want to do is I want to align my coordinate system in the direction of the velocity. So that's going to help me think about this radial component that points towards the center of the circle and this tangential component that points in the same direction as the velocity. So what I'm thinking about is not necessarily a plus x or a plus y. I'm thinking about the component of the acceleration that is parallel to the velocity, because that's going to tell me whether the object is speeding up or slowing down, and the component of the acceleration that's perpendicular to the velocity, because that's going to tell me how the object is turning. That component that is parallel to the velocity is the tangential acceleration. And so again, that has the same structure as our previous equations in that the tangential acceleration, that component, is equal to r, the distance from the axis to the point that's rotating, times the angular acceleration of the wheel. And again, this indicates whether that object is speeding up or slowing down as it rotates. The angular acceleration points out, which of course tells me that since it points in the same direction as the angular velocity, that sure enough that wheel is spinning faster and faster as it rotates, which is part of what the tangential acceleration piece already told me, was that because the tangential acceleration points in the same direction of the velocity, that means that this point is spinning faster and faster, and that only happens if the wheel is spinning faster and faster. The second component is the radial acceleration. And again, it's the component of the acceleration that's perpendicular to the velocity, and it's got a slightly different expression. This is the radial acceleration component is equal to r times omega squared. And oddly enough, using our expression for omega from the previous slide, so how omega relates to the linear speed v, omega squared is just v squared over r squared. And of course, this r cancels one of those, and I'm left with v squared over r, which is the centripetal acceleration. So we have seen the radial acceleration before, and sure enough, it still indicates the same thing. It's indicating whether or not your object is changing direction because it points towards the center of the circle that your object is spinning along. I have two components, so if I want to know the magnitude of the linear acceleration, that's simply the tangential component squared plus the radial component squared. Take the square root of that. And then again, if I want to know the direction relative to the direction of the velocity, so the direction of the acceleration relative to the direction of the velocity, then again I can solve for this angle phi by taking the inverse tangent, and I just want to put the tangential component on bottom, the radial component on top. So the last detail is how these quantities relate as vectors depends on a cross product. We talked about how the linear speed relates to the angular speed, but if you want to think about how the linear velocity relates to the angular velocity, it's given by this cross product. And so part of what the rules of cross products will tell you is not only now how their magnitudes relate, that was the equation we were looking at before, but also which direction these vectors need to point in relative to each other. So using our right-hand rule, you can see that omega pointing out, r pointing up and slightly to the right is going to give you a velocity vector that points in the direction it's drawn on the page. The linear acceleration is defined by not just this cross product, which gives us the tangential component. So alpha cross r gives us the tangential component of the linear acceleration. But you also get this radial component by thinking about negative omega squared. And the negative here is just telling you that r is always drawn out from the axis of rotation, and the radial acceleration always points back towards the axis of rotation. So that's why that negative sign is there. In terms of magnitude, the tangential component being r times alpha, that is the magnitude of that cross product because these two vectors are always perpendicular to each other. The magnitude of AR, well again, the magnitude of this is just r times omega squared. We don't worry about the minus sign in terms of thinking about magnitude. So you can see that the magnitude equations we were looking at before are embedded within this vector statement. But now this gives you not just information about magnitude, it also gives you the complete information about how the direction of the acceleration relates to the direction of alpha and omega.